Hi everyone. This video is going to give you a little bit more information about valence electrons and ion charges within the periodic table. This is crucial information that you'll need to understand in order to do ionic bonding and then ionic naming of compounds. So I want to switch to my slideshow here. Okay, so this is just a little bit about electrons. You know already that they're arranged in shells. These shells are called energy levels. So each shell is an energy level. The outer shell, whichever shell that happens to be, because they can have multiple shells from 1 to 7, or if they're in an excited state, they can have more. Those are called valence electrons. Valence electrons are really, really important. They are the things that make all chemical reactions happen. They are the things that make all physical properties of an element, the physical properties. So valence electrons pretty much dictate everything. The inside electrons are also important, but they're just kind of there and they're just floating around in their shells. The valence electrons are the ones that actually get shared or transferred to other things. They're the electrons that are super important. And so if they're shared, then it makes a covalent bond. That's a molecular compound. You'll learn a lot more about those later. And then if they're transferred from one atom just clear to another atom, that's an ionic bond. And those form ionic compounds, which have different properties than covalent compounds. So the question is, how many valence electrons are in, each element? And so you can determine that just based on its group in the periodic table. So if you remember that this is group 1A, right? And this is group 2A, but then these are all B groups, so we don't count these. Okay, we don't worry about these right now. This is 3A, and then 4, 5, 6, 7, and 8A. Okay, so each one of these has the same number of valence electrons as its group. So this one has 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, and 8 valence electrons. That's supposed to be an E. Okay, so those are very easy to figure out. The B groups are not as straightforward, so we don't talk about them when we first learn chemistry. And the reason that these have this number of electrons is if you look at sodium, for example. Okay, sodium has 11 electrons. So we have 11 protons, 11 electrons. We can only fit 2 on the first shell, remember? 2, and then we have 1, 2, 3, 4, 5, 6, 7, 8. Now that's 8 on that shell plus these 2. That's 10. And now we have one more shell. We have to put one more electron on it. And then he's all by himself out there. That's 11 electrons. He's a real jerk, and all these other electrons want to eject him out of the atom as fast as possible. The only thing keeping him there at all is the protons inside. The protons are positive and this electron is negative. And they're going, oh, stay, we like all of our electrons. But this one guy, he's just such a jerk that they pretty much eject him out pretty fast. On a small atom like sodium, he's ejected pretty fast. On a much bigger atom like cesium, where there are 6 rings, the protons can't even hold on to him for a second. He just goes so fast that the whole atom makes an explosion as soon as it gets rid of its electrons. So that's why they react that way. Now, the same happens with magnesium. Magnesium has 12 electrons, so that means you're going to have 2 on the outside ring. Aluminum now has 13 electrons. There's going to be 3 on the outside ring, so you can see how that goes across. Okay, and that will be the same for each column. This one will always have 1 electron. This column will always have 2 valence electrons. This column will always have 3 valence electrons. 4 and 5 and 6 and 7, and this column will always have 8 valence electrons. Now that's really important because these guys are the most stable atoms in the whole world. They don't react with anything because they have enough electrons and they're very, very happy the way they are. So let's move on to the next slide here. Oh, I have to turn off my pen. Okay. So now, how many valence electrons you can see again that there's the same number as the group. And when we do this, when we write these are called Lewis dot symbols or Lewis dot structures. Okay, and this is the way they're written. They just show the valence electrons. 1 dot for each valence electron. So we have 1, and then lithium has 1, right? Beryllium has 2. Now, this is important to realize that when you do this, you can't put them together. So beryllium has 1 over here and 1 over here. Now boron 1, 2, 3. Carbon 1, 2, 3, 4. You can't start pairing them up until you have more than 4. 1, 2, 3, 4. Now you have to pair this one up. 5. That one has 5. Same thing with oxygen. You put 1 around each, right? 1, 2, 3, 4, and then you have to pair these up. 5, 6. It doesn't matter which side they're paired up on, or or anything. But the important thing to realize is that it has to be kind of in a box. It's almost like this. Like the electrons have to be in the box or on the box. So there's 2 here, there's 2 here, and there's 1 down there and 1 down there. But they're not in a circle. That's what's really important. They're not in a circle. So if you go all the way over to neon, you'll see that it has all 8 of its electrons. Back to sodium, it has only 1 valence electron. These show only valence electrons, though. Okay, that's really important. So again, these are called Lewis dot symbols. So you will see these. We will revisit them in another chapter later. All right, so valence electrons cause ion formation. So everybody wants to be like the noble gases. They all want to have a filled electron shell. So for metals, like sodium, let me draw the sodium one again because that's a good example. So we have the 2 electrons, and then we have our, oh gosh, I'm really bad at drawing. We have our 8 electrons. I can't even draw a whole circle. Okay, and then we have this last ring with just 1 electron on it. Remember, he's a jerk, and they need to get rid of him. So in order for it to have the same number of valence electrons as the nearest noble gas, what we would have to do is we would have to make this electron go away. Okay, and that means this whole ring would go away. All right, so that would go away. And now if you look here, if I erase this, you can see that if we have that 1 electron go away and that whole ring goes away, now we have a full outer shell. See, now it's sodium with a +1 charge because it has lost an electron, and now it has a full outer shell. So it's very, very happy that way. So it goes towards the losing electrons. The only other way it could get to a full shell is if it was to gain 7 more electrons, and that's just too hard. But on the other side of the periodic table, where you have, say, like fluorine, okay, that has 9, right? So we have 1, 2, and then we have 7. 1, 2, 3, 4, 5, 6, 7 electrons, right? 7 valence electrons. Sorry if these aren't very clear. In order for it to get a full outer shell of 8, it's easiest for it to gain 1 more electron. Okay, so it's going to take it from somebody who doesn't want it very much. So it's going to take it from like sodium or, something like that, potassium. And so that extra 1 electron will make a fluorine -1 charge, and it's very happy that way. So that's what they're trying to do. The ions will all be made because it's trying to get to 8 electrons. It's called the octet rule. Okay, so if I show you this. Now, again, all atoms want to be like noble gases. This is neon. Neon has 10 electrons, so there's 2. Oops, I gotta go back. Oh, back. Sorry, there's 2 in there. Let me write in red. We have 2, and then we have 8 on the outside, so it's a full outer shell. Full shell. Okay, that's called a full octet, and it's an octet because it has 8. Okay, so in order to do that, they have to, all the other atoms don't have 8. They either have to gain electrons or lose electrons to get there. So atoms with 5 or more valence electrons, which means in group 5, 6, or 7, they will want to gain electrons to get to 8. So oxygen normally has 6 valence electrons, but it's going to gain this guy, and it's going to gain this guy to get to the 8 valence electrons. Now it has a full octet. So oxygen is going to have a 2- charge so that it can gain the electrons and be the full octet, and then it'll be very happy. So oxygen will always make a 2- charge. Let me click here and here. Okay. Okay, atoms with 3 or less valence electrons. So this is like metals, right? Group 1, 2, or 3. They're going to lose electrons. This is the sodium one that I showed you before. You got the 1, 2. You got the 1, 2, 3, 4, 5, 6, 7, 8 here. Oops. 8 electrons here. And then you just got this one lonely guy in the outer ring. But in order for them to to get a full outer shell, you have to just like lose this whole electron and lose the whole ring, and then the rest of the rings inside are a full octet. So it works even if the first ring is the full one. Like for instance, if you have helium only has 2 electrons, and it's, you know, it's still happy because that first ring is 2, and it's happy with it's full no matter whether it's 8 or 2. That's called the duet rule. And then lithium is 1 more away from there, and if it loses the 1 electron, it goes back to just the 2, and it's still very happy because it has to have a full shell. So that's the whole point of that. Okay. All right. So if you look now, we have patterns here that happen. Everything in group 1A will form a +1, you know, +1 ion. Everything in group 2A will form a +2 ion, okay, because they're going to all lose 2 electrons to get back over to the noble gas. And everything in group 3 will lose 3 electrons to have a +3 charge. Okay, so it's really helpful to be able to have that. Like these are all 1+ charges, these are all 2+ charges, these are all 3+ charges. Now over here in group 7A, they're all going to gain 1 electron because they have 7, right? So they're going to gain 1 electron, so they're going to end up with a -1 charge. These guys are going to end up with a -2 charge. And these guys are going to end up with a -3 charge. Now, if you notice, we don't have anything in the 4A column. These could be plus or -4. They could have other charges. They generally don't form ions at all. They share electrons a lot. So we don't really talk about them when we're doing this, just like we don't talk about their transition metals, because they don't always act the way we'd expect them to when we're just learning chemistry. So we're going to stick with just the main group ones that are +1, +2, +3, and -1, -2, -3. So you should label your periodic table like this, that group 1A is going to have +1s, and group 2A is going to have +2s, and group 3 is going to have +3s. And then it goes -3, -2, -1. And the noble gases do not form any ions at all. They will not form an ion. They will not lose an electron. They don't want to share any electrons. They don't want to give up any electrons. They don't want to accept any electrons. So they're just not going to form any ions. That's kind of why they're noble gases. All right. All right. So when you get a question like, what does it mean to achieve an octet? It really means how many electrons is this atom going to gain or lose when it forms an ion? So you kind of know the answer to this already. We just sort of went over it a bunch of times in a bunch of different ways. So aluminum is a metal. All metals are going to lose electrons. It's like the definition of a metal, okay? Metals always lose electrons, okay? And they're going to always form a positive charge. So it's probably going to ask you what charge is it? And you can't just say positive or negative. You have to give like a positive number, like a +3, right? How many electrons is it losing? It's losing 3 electrons. Now, nonmetals, on the other hand, they're going to gain electrons. Nonmetals gain electrons, okay? And they're always going to make a negative charge. Now, again, you can't just say negative. You have to say, like, what kind of negative? This is -2 because it's gained 2 electrons. Now, remember, you're trying to get to 8. Aluminum has 3 valence electrons, so it's going to lose those 3. Okay, oxygen has 6 valence electrons, so it's going to gain 2 to get to 8, right? Lose 3 gets you back to 0, which underneath that shell is another 8, and then gain 2 over here is to achieve the whole octet full. Okay, so I hope that helps a little bit. If you have any questions, please contact me. I'm here to answer any questions for you.